So today we're going to be talking a little bit about vectors and scalars, and primarily focusing at vectors and scalars at grade 10 level. At this point in grade 10, you're only supposed to know how to work with vectors in one dimension. I think in grade 11, that's when you're going to start working with vectors in two dimension. And I think if you move ahead with physics post school, then you're going to start doing vectors in three dimension. But for our discussion, we only need to concern ourselves for grade 10 with vectors in one dimension. So vectors are actually an important, vectors and scalars basically are very important. It's very important for you to know how to work with them, especially vectors, because I think they form the basis of mechanics. And if you know how to work with vectors, it's going to make your understanding of physics much better. So without wasting any time, let us start off our discussion by doing a simple exercise. So I'm going to draw two columns over here, and then in these columns, I'm going to write a few statements, maybe four each. So let us say, I don't think this is going to be enough space. So let us say in our first statement, we have a statement that is saying to us that the second column will be on this side. So we have a statement that is saying to us that a car was moving at a velocity of 20 meters per second eastward. East. I have a terrible handwriting. Eastward, right? And then the second statement maybe says that a box was displaced 50 meters west. 50 meters west. Maybe the third statement says that a force of about 10 newtons was applied downwards. Yeah. And then the last one, maybe the statement says something like what is it? And a car was accelerating at accelerating at 5 meters per second squared to the right. And then I'm going to take another set of statement. So assume here we have two columns. 1, 2, 3, 4. And then maybe in this statement it says that an object with a mass of 20 kg. So mass of 20 kg. Maybe it says that when you measured your temperature, your temperature was 10 degrees Celsius. Temperature of 10 degrees Celsius. And then maybe it says that you traveled a total distance of what is it? 10 meters. And lastly, it may say that you were traveling at a speed of 40 kilometers per hour. Just stay with me. This is all going to make sense. So now I want you to look at these two columns that I've drawn here. And I want you to try to find if there's actually a difference between the statements on this side of the column and the statements on the other side of the column. What is that difference? What do you think the difference is? I hope this is clear. So what do you think the difference is between statements on this side and statement on the other side? So you would have noticed something. So we're talking about various physical quantities. So we spoke about velocity is a physical quantity, displacement, force, acceleration, mass, temperature, distance, speed. All of those are what we normally refer to as physical quantities. There are many others. There's energy, there's power that you're gonna be working with in physics, right? And then we've spoken about them. But interestingly, on this side, when we mention the physical quantity, we include them its magnitude. So how much of it, its size, as well as its direction. Where is it going? Where is it acting? But on this side, we talk about its size or magnitude, and we don't make any reference to to its direction. We spoke about displacement, and we said it was 50 meters west. Same thing, we said the force of 10 newtons was acting downwards. That's the direction, right? Something can go up and down. That's the direction. It was accelerating at 5 meters per second squared to the right. So something can either go right or left, right? Okay, cool. And then here we said a temperature of 10 degrees. So you can never ever say a mass of 20 kg up. That makes absolutely no sense. Or my temperature was 10 degrees to the left. You can already see it makes no sense. And also distance, when we report distance, we also only include its size. Same thing with speed. So what did we notice? For statements on this side, we mentioned the magnitude, or for physical quantities on this side, we mentioned the magnitude. They have magnitude plus direction. And these ones here only have magnitude. There is no direction. Oof. Is that the spelling? I hope so. No direction. Right? So now how do we define these quantities that have magnitude and direction? That's what we call vector quantities or vectors. So they are physical quantities that have both magnitude and direction. And then on the other hand, for those physical quantities that only have magnitude but no direction, we call them scalar quantities, or what we call scalars. So I'm hoping, in terms of definition of what is a vector and what is a scalar, you now have a little bit of an understanding. So what does this mean? This means that velocity is a vector, displacement is a vector, force is a vector, acceleration is a vector. There are many others. I'm not going to be able to cover all of them. And then on this side, mass is a scalar quantity, temperature is a scalar quantity, distance is a scalar quantity, as well as speed. Correct. So now let us move on and do a little bit of a calculation quickly. Okay, so let us now say you were pulling a block of wood for some reason. So to represent that block of wood, we draw a block, and you were pulling it with a force of about 10 newtons. So let's say your applied force was 10 newtons, and you guys were moving to the right. So you were pulling it in this direction, right? So it's a block of wood and you're pulling it, right? And you're pulling it maybe on the ground, right? So maybe you're pulling it in this direction. And then we know that most surfaces have friction. So friction is the force that actually opposes motion. So if you're going in this direction, friction is actually pulling you in the other direction. So let's say the friction between this block of wood that you're pulling and the floor, this is the ground, it's a bit rough to show this friction, and that thing, the value of it maybe was, say, let's say it was Fr for friction, in this case was 0.5 newtons, right? All right, cool. So now let's say a question says calculate the resultant force. So question says determine F resultant. Would you go about doing that? So first of all, to define what we mean when we talk about a resultant. So a resultant, the way I like to understand it, it makes it much easier. It says that if you add all of the vectors, it's a vector you get when you add all of the vectors acting on an object. So in this case, we have two forces acting on this object. We have your applied force and your, what is it? Your friction. So when you add all of them together, whatever value you get, that will become your resultant vector. But there's also a standard, let me look for it. There's also a standard definition of it that says to us it is a single force, or what we call a resultant force. It is a single force or vector having the same effect as all other forces acting together. Same thing. But the important thing for you to remember is that when you add all of your forces acting on a certain object and you get a certain value, that value we call the resultant. So what is that telling me? That is telling me that if I add my applied force plus my frictional force, I will actually get my resultant vector. But it doesn't end there. There's an important thing for you careful about. When we talk about vectors, we always, that the fact that it has direction, it means that you have to determine which direction is positive and which direction is negative, right? So for me personally, I like saying it doesn't matter which direction you select as positive and which direction you select as negative. The most important thing is that you're just consistent in your calculation. So for me personally, I like to say the direction of motion, and we said this thing is moving to the right. So my direction of motion, which is to the right, I would say it is positive. And then direction that opposes motion, which is to the left, I would say it is negative, right? And you'd see why now. So if you are pulling this block at a force of 10 newtons, and somehow this friction is acting against you at a force of 0.5 newton, it will be almost as if you're pulling this block at actually a force of 9.5 newtons, which would be our resultant vector. But then how do we get that 9.5 newtons here? So we say, okay, FA is positive because it's acting to the right, plus FR, it's acting in the opposite direction, it's going to become negative. So the magnitude, the value that we have for the magnitude, we'll have to put a negative in front of it, right? So then in this case, we get 10, that's FA, minus, remember, a positive multiplied by a negative becomes a negative, minus 0.5, which will then give us 9.5. And you notice that that 9.5 is actually positive, meaning that my resultant is actually moving to the right. So you have to include the direction. You have to include the magnitude as well as the direction. So that's normally how you find a resultant vector. And then something that most people struggle with is in terms of how do we then sketch this scenario. So now we found the resultant force algebraically by using this equation, but then how do we graph them? So we're going to use something called, what is it? We're going to use a method called the tail to head method to sketch these vectors. So remember, when we draw a vector, when we represent a vector, when we sketch it, we just normally draw a line with an arrowhead, right? And we call this end here with an arrow, we call that the head of our vector. And this part here, we call it, what is it? The tail. So now let us try to, okay, before doing that, so there's an important thing that you have to know, especially in terms of drawing this vector. Two things. So when I draw vectors, let's say I call this F1 and I draw another, let's assume that they are the same size, right? F2. To show that they are the same size, I'll make sure that the length of these vectors that I have drawn is the same. So this would imply that F1 is equals to F2 and they're all acting in the same direction. And now, if they can also be the same size but acting in opposite direction, right? So F1 equals to a negative of F2. So this one is acting the other direction, this one is acting the other direction. Same size but different magnitude. However, I can also have a case where maybe F1 is slightly bigger than F2, right? So by the length of this one, if you draw a vector and you show the length of the other one to be bigger, what I will assume is that you're saying that F1 is greater than F2, the magnitude of them. So it's just an important thing to note about these vectors before we go on to drawing, what is it, the vector, to try to represent this situation, graphing them using the tail to head method. Okay, let us do that. When you're using the tail to head method, let me say I will select my 10 newton vector as my first vector and I'll draw it and I'll say it's FA. So according to the tail to head method, when I draw the second vector, I have to draw the tail of the second vector, which is FR in this case, at the head of the first vector. So this is the head of the first vector. So here I have to draw the tail of the second vector. So the tail of the second vector will somewhat be here. So somebody might say, I can just draw it here. And it's smaller because remember, its value is like 0.5. But you see, it doesn't look nice. So normally what we decide to do is that, no, let me just draw it below it so that at least it looks a bit clean. Okay, I don't know what happened there. So that at least it looks a bit neat, right? So I'll just draw my second vector, and it will be the head of the tail of the tail of the second vector will be at the head of the first vector. So it will somewhat be there. Now I'll call this FR. And as you can see, it's still acting in this direction, and FA is acting in that direction. To now draw the resultant, you will say the tail of the resultant will be at the tail of the first vector. Remember, FA was our first vector. So its tail will be here, and then the head of the resultant will be at the head of the second vector, and this, or not second, or our last vector. If you have three vectors, it will be at the head of the third vector. So then you will draw it. So and then you say this is F resultant. So you see our resultant vector is still acting to the right. I hope that made some sense. Let us now take another example. So let us say in this case, there you were with your friend of yours, and you were pulling this block of wood, both of you pulling to the right. So this is your force, you pulling it at a force of 5 newtons to the right, and then your friend is also pulling at 10 newtons. So F2, 10 newtons to the right as well. So let's say direction of motion is positive, which is to the right, then negative is direction opposite, and say it was a frictionless surface, so we don't consider friction in this instant. And the question says calculate the resultant vector, right? So we can do it algebraically as before. We would say F res would be nothing but F1 plus F2. Both of them are acting in the same direction, which we decided that it's positive to the right, so we don't need to include that negative. So this is just going to be 5 newtons plus 10 newtons, which is going to give us 15 newtons. It's positive, meaning it is to the right. You have to include to the right because force is a vector, unless you are asked to only find the magnitude, right? Cool. Let us try to do the same thing graphically again, the same situation. So let us pick let us say F1. So we draw the first vector there, it's 5 newtons, it's F1. And using the tail to head method, we know that the tail of the second vector would be at the tail of the first. The tail of the second vector will be at the head of the second vector. This is the head of the first vector, so the tail of that one will be here, and it's quite longer. It's 10, remember? And then to find the resultant, we say the tail of the resultant will be at the tail of the first vector, and the head will be at the head of our last vector. Our last vector in this case is F2. And then this is how you would find your resultant. Somebody else might draw it just here, but then if you're using the same color pen, you're not going to be able to see what is what. So this would be F2, and then this would be F resultant. Right? Let us take a question quickly from a previous question paper. I found one that was quite interesting. Okay, so we have a question over here, and it is from 2012. So it says that which one of the following physical quantities is a vector, right? So we have the options that are given to us is time, speed, velocity, and distance. And we already discussed that time is not a vector. Definitely time doesn't have direction. Speed doesn't have direction. Only velocity has direction. So meaning the answer here will be C. A question that I wanted us to actually focus on, let me do this quickly, is this question. I find this question to be quite interesting. Hope you can see my screen. So it's question 2, and it says that a crane lifts a crate vertically upward as shown below. And it says that the total weight lifted is 1,480 newtons, and then the crane applies an upward force of 1,550 newtons, and then there's also a frictional force of 20 newton acting on the crate when it's being lifted, right? And I think it's also important to notice that, what is it? I'm trying to think. So they've given us a sort of a schematic diagram there, and they're asking us to define the term resultant of a number of forces. We've already defined that. 2.2, calculate the magnitude and direction of the resultant force acting on the object. Cool. So what is it that we're supposed to do in this instant? What we're supposed to do is that we're supposed to now find the resultant. We have a force of 1550 acting upwards, a force of weight acting down, and then we have also frictional force that is acting up. So let us try to actually solve this problem quickly. So how are we going to do that? Let me see. So we're going to do this by saying, okay, so we have force, a block. So we have a block over there, and we have a force that is moving upward, and that force is called F, and its value is 1550. We have a force again of weight. This is wrong because now you see I drew the length of this force of weight to be greater than this one, and what that was implying was that I was saying that the weight is actually greater than the applied force, which is not really true, right? So you do that, and then also I forgot you have a friction there, which is 20 newtons. So to find the resultant, so let us say up is positive, so that's the direction of motion, that's the direction at which our block is being lifted, and then down is negative, and then we find the resultant force. We'll say it is F plus our friction. So remember, it's the sum of all of those forces acting on the object plus the weight. But then we said that down is negative, and we know that friction is acting downwards, so it's going to be negative F plus negative weight, because also the weight is acting down, right? And now it's just a matter of calculations. F is 1550 plus, it's going to be plus, multiplied by negative is going to give us positive minus 20 minus 1480. This together is going to be 1500. So meaning our force is actually going to be 50 newtons. It's positive, meaning it will be acting upwards. And the last thing, I know it wasn't asked in the question. If you were asked to now draw this schematically, I didn't want this lesson to be so long, but it's fine. If you were asked to draw this graphically, so you would draw your force, your first force, using the tail to head method, right? And you'd call it F. And then the tail of the, maybe this is your second force of vector, the tail of it would be at the head of this one. So it's quite small, so we call this F. And then the tail of your third vector would be at the head of this one. So draw again, perhaps, and then this will be your weight. And then to draw the resultant, would say the tail of the resultant has to be at the tail of the first vector, and the head has to be at the head of the last vector. Our last vector was the weight. So your resultant would look something like this. Resultant. So this is how you would normally represent that situation. And yeah, this brings us to the end. I hope somehow this clears any confusion you might have about vectors and scalars.